Good morning, everybody. I'm just getting this up and going for you here. Okay, so last time we checked in, there was a lot of pieces related to things we use every day and the optics elements in terms of the lens used in those devices. So, what I'm going to go back and talk about today is some of the questions I assigned from the textbook. I've got some pictures and little story elements to talk about related to the invention of particularly the microscope and the telescope. And then I'm going to show you the last piece, which is to talk about the diverging lens. There's only one ray diagram there. And then I am going to include a Google quiz for you to try related to these topics this week. And then we'll start with some new stuff next week. Debating some stuff, how I want to do that. But anyway, for another time. Okay, so in your textbook, most of the questions are related to the microscope, which is actually quite tricky, and the images in your textbook probably were not helpful. So the first question, number 2, is about the size of the aperture and the amount of light that can be collected by the camera. So think of this like the pupil of your eye, aperture being your pupil, and so the wider or more open that is, the bigger the circle that is, then the more light will get into the camera, and vice versa. Going on to the next one, the next couple ones are microscope, about the arrangement of the lenses, and then using a ray diagram to look at that. So that one I want to look at one more time. This is the most complicated ray diagram you would see. It's sort of an extension. It's extra. So don't feel too bad if you're finding this challenging. It is challenging, but also sometimes challenges are good. And I like if some of you are up for this particular challenge and to try it. It would be like a bonus type thing on a test. It's not expected to sort of be where you start and build on. This is like the end of where we would take our optics and our ray diagrams. So I'm going to put a better image of what I showed you at the end of last class under the camera here. Let's move this around for a second. Hoping you can see that. And I'm going to walk you through what I've got here. Okay, so the microscope has 2 lenses that line up with each other. You have the one on the eyepiece, and then you have different ones on the nose piece that you click into place. But whichever one you click into place, the idea is the light goes through the lens on the nose piece, then comes up and goes through the lens in the eyepiece. They have different magnifications, which means they're engineered to have like different numbers of magnification. They'll have different focal points. So I have 2 converging lenses here on the same principal axis. This is my object on the stage. So the thing on the slide that I want to magnify and make larger. For this lens, I've picked an F, a focal point. Ideally, you would measure to make sure that the distance to this F is the same as to this F from the optical center of the lens. And then I have this one as well. You can see it's F here, and this F here. I've chose to make the focal point on that one a little bit longer. It allows me to get a bit more of the effect I want here to show you today. Okay, so how you would start this is my object. When you're doing ray diagrams, unlike just generally talking about something, you pick one point on your object. Generally, the top one is the one that we have taught you to follow. It'll work for you every time in all the cases we present to you. Okay. So when you make a ray diagram, you have 3 different rays that you can choose from. You need at least 2 to find your image. The options are to go parallel to the principal axis, get to the center, and then turn and go straight through F on the other side. Or to go straight towards the optical center and continue out straight on the other side. Third option, which I did not elect to use here, but I could have, would be to go from the same point, draw a straight line through F till I get to the center of the lens, and then turn and go parallel to the principal axis. Okay, this is the most like physics we're going to get. It's very precise. It's very detail oriented. Lines being straight are important. Turning at the right point is important. Paying attention to exactly where they cross is important. And physics also comes with a lot of mathematical pieces. So I think next week I'll show you a little bit of that, just for those of you that are going to take physics, to just get a bit of an introduction to what that feels like, because this is the closest we're going to get. Okay, so I chose those two lines, okay, from my three possible options. They crossed right here, so that is equivalent to this point on the object, and then I have to draw back to the principal axis to see that image. So my image is inverted, which means it's upside down from how it started. It's already looking a little bit larger than it was to begin with. If I measured the height of this and I measured the height of this one is bigger. And its location is on the other side of the lens that I started with. And it is real if I wanted to at this point. However, we're going to keep working with it. So now I have another lens here. And what I'm going to do is take this image and treat it as the object for the next lens, because the light is going to go now off of this and create a second image from this one. So I'm going to treat this now like the object, and I'm going to do the same thing I did before. So I'm picking two light rays from my options. You'll see that this one is inside F for this lens, so it makes sense that I would do the one that goes parallel and then turns and goes out at the other side, and the one for the optical center. Okay, these ones are going apart from each other. They are not going to cross on that side. So then what I have to do is I have to do some dashed line extensions back to see where the lines are going to cross, and I find they meet right here. So then I once again know that that is the same as that, and I draw a line back to the principal axis. And now I can see an image that is actually in the same orientation, same attitude as this one. So it would be considered upright compared to this one because they're pointing the same way. It is definitely larger than what I had to begin with. This one is virtual because I had to extend these back, and the location is the same side of the lens as the object. So if we just step back and reflect on the whole thing for a second and think about what a microscope is supposed to do. A microscope is supposed to magnify what you're looking at to make it larger. And I know I've done this right because what I finished with here after going through both lenses is something much larger than what I had to begin with. The other thing that helps you know you're on the right track is that just from experience, you know that microscopes do everything backwards. So as I push right, the image goes left in my field of view. If I push the slide away, it moves towards me in the field of view, which is what you see through the eyepiece. So overall, this has come out what I expected to be. Compared to the thing on the stage, it's upside down. Compared to the thing on the stage, it is much larger. Okay, so I just want to walk you through that one more time because it was a question I left you with, but it's actually quite complex, and my diagram was probably squashed and not so easy to see. All right, so I hope that was helpful for that. And then the other questions are sort of related to what these devices have done for us in society and how they've changed our perception of the world. So the first one, how is being accessible to things like telescopes and microscopes affected how we see the world? I'm going to take this away for a second. And I'm going to show you, first of all, some pictures of different types of telescopes because we've only talked about one particular type. We'll see how this works out under the camera here. Just going to move that over there for a sec. Bear with me while I do some page flipping. This one's pretty dark. So here is a kid looking through a telescope. This is my book, My Short History of Nearly Everything by Bill Bryson. You know how I sometimes read from different things. This is one I've used a few times. This is my my illustrated version. So here we have a kid, and this telescope is like the one that I was describing, where you have two lenses. There's going to be a lens here, and there's going to be a lens here where you put your eye. These two things combined, like the microscope, will make whatever you're looking at look larger than it actually is, and it will be upside down, whether you realize that or not, just like the microscope. Okay. Now, there are some other styles of microscope. These ones uses glass lenses. So let me back up here. And we didn't have these devices always because it's quite a skill to make pieces of glass and engineer them to do these things. So it's an art and a science in terms of making the pieces of glass, and it took a while for people to develop those skills and get quite good at it. Lenses, pieces of glass can get quite heavy though. So you get telescopes that look like this, and we're going to talk about mirrors too coming up. So this one, the piece of glass is probably getting too big to have up here at the top. I'm pretty sure this one, could be wrong, it does not have a big piece of glass up here. It probably has some mirrors in it, and you look sort of through the side. So these ones that you might be familiar with if you know about telescopes, I kind of there. Oops. There's no glass up here. This is working on a different system, which we'll talk about later. So the kind of telescope that I described to you is the refracting one so far. Okay, where you have a big piece of glass at the end and then a little piece of glass by your eye. But there are different designs in telescopes because glass, as you get larger and larger pieces, gets really, really heavy, and so you can't have it at the end of something that you're holding up to the sky to view. So if you're familiar with like telescopes that would be housed in something like that, okay, those are not going to be that style of telescope. Mm-hmm. But when telescopes were invented, it allowed people to see planets in ways they hadn't been able to see before, see moons of planets, all those kinds of things, help confirm motions in the sky, which would have translated back to understanding things about our own planet and our place in the solar system. Okay, the other thing I want to talk about, the microscope, a little piece from here. I wanted to share with you the fact that the microscope also created a new perception of the world. Basically, we began to see microscopic life, two words there together, things that are smaller than what we can see with the eye and that we didn't realize were life forms that existed out there before. So let me just change what I wanted to look at here for 1 minute. I wanted to say, this is the worst. I lost my spot. Okay. One of the first things that people looked at was plant cells. And cork was one of the first plant materials that got looked at closely with a microscope. And like cork, in a wine bottle, it actually comes off a tree, cork tree. It's under the bark. You take that off. So when they looked at that, they saw these like little squares. And Hooke, who was the scientist who was looking at that, thought that those little squares, which were actually the cell walls, looked like little jail cells or monastery cells, actually probably monastery cells. And so he called them cells because those looked like little rooms to him. They were empty because they would have been dead. All the other stuff was not inside. Okay, so then we have this other scientist who came along and was able to create his own instrument, self-taught, which was like a paddle-shaped microscope. I'll show it to you. It's a really odd little thing there. See that? And he was able to take some remarkable, do some remarkable drawings about what he was seeing through his own microscope. So I had it here. He had reports. He sent out reports and intricate drawings on things that people had never really seen fully examined before, like bread mold, a bee stinger, blood cells, teeth, hair, his own saliva, and some other bodily fluids, things like that he had looked at. Basically, nobody knows how he got such magnificent magnifications from his simple handheld devices that he built himself. Basically, had tiny bubbles of glasses embedded in them. And I want to find how much more he might. Oh, here we go. So when the Royal Society started to get his drawings that he was sending to them, he was getting magnifications of up to 275 times. Little formal education, no background in science. He was just really dedicated. He was an observer. It's technically brilliant to be able to put something like that together to build that, and just very perceptive. And so that would be 17th century, I believe. And so they were getting magnifications of 30 times until Antony van Leeuwenhoek, I don't know if I'm pronouncing that right, got his magnifications of up to 275 times. Okay. And so, of course, you would start to see bacteria. In 1683, he discovered bacteria. And that helped people understand a whole lot more about why people were getting sick. Because people could not before see things in the water supply, for example, and understand that it was not just, let's say, evil spirits or curses or things like that that were causing problems, but actual tiny little things that nobody had been able to see before that were having an impact on people. Okay. Light microscopes are only so powerful, so just like the telescope, you can only rely on glass lenses to a point, and then you have to switch to something else. So we have electron microscopes also in use, way more powerful than the light ones, and they are allowing us to see viruses. The viewing of viruses came along much, much later, 19th, 20th century. Oh, I was going to mix it. In the 1900s, let's just do it that way, is when the electron microscope began to be developed and allowed us to see viruses, and then even further down into things like molecules and certain large atoms and things like that. Okay. So I hope that helps address some of those more extension societal things. Number 22 was about the increased use of cameras and how that's affected society. So some students would have responded talking about security, surveillance, all those kinds of pieces, and what that looks like now and how that has changed people's behavior. Okay, we are going to do a really, really short note today. It's just on the diverging lens, and then that is a good place to end for the week. So, note paper, and we're going to do ray diagram for a diverging lens. Okay, so these are the ones that come in at the center, also called concave, okay, because they go in like a cave. Let's do principal axis here. And so I'm going to draw a concave lens, like doing my best to be symmetrical. Probably failing, but that's okay. Ugh. There we go. Let's put that as the center. So both of those should be the same. They're not, but you get the idea that we have a concave lens here. It would be pretty thin. That doesn't look so thin. That's okay. So we've talked about before how with this kind of lens, if I put an object, let's say right here, when the light rays get to the lens, it spreads them out on the other side. So instead of bringing them into a point, it spreads them out. So the focal point is on the same side, which seems weird because if you think of things spraying out like this, and then I trace backwards, they're going to come from a point here instead of heading towards a point over here. So we are going to put F there. Think of it as like the light rays are going to spread out on the other side, but if I trace them back, they would come from there. And F on the other side, but it should be exactly the same distance, but I'm not measuring because light could be coming from this way as well. And so because it's a lens, it's going to have the same thing on both sides. All right. So Like before, we have some options for these light rays. I'm going to do the one that goes straight towards the glass first. Gets to the center, put an arrow here that shows I headed out straight, parallel to the principal axis till I got to the center of this piece of glass. Okay. Now what's going to happen is instead of this turning it and going towards F, that would be what a converging one would do, it is going to head out. And I get the angle that it heads out at by using a ruler. And if I had a line that went from that F, it would head out as if it came from F. Okay, because all these spread out lines are supposed to sort of come back together to give you a point of origin or where they started from. Right? And then I'm going to choose the through the optical center one. I'm just going to turn this a bit so I can try and do a straight line for a second. And it will still go straight, just like in the other. There we go. Oh, I hope that's straight. Ugh, it's not so straight. This should have been straight like this. Okay, so it keeps going. We see they're not going to cross. So then what I do to find where the image is I do this backwards extension again. So I'm going to draw in how this one came from F. We see that one that headed to the optical center, and there is where they cross. So this is the object, and this is the image right in here. Okay, it's going to turn out this way every single time for the diverging lens. So let's do the SALT, the properties of the image, these 4 pieces to the image. S stands for size. So every time you use a diverging lens, the image turns out smaller than the original object. The attitude is upright, which means the arrow is still pointing in the same direction, pointing up here, pointing up here. The location is the same side of the lens as object. And in this case, it's between the lens and F. I could add that, I just ran out of room. Okay. And the type would be virtual. It's virtual because I've had to use these backwards dash lines to find the point of intersection where they crossed to find the image. I cannot capture that on a screen. So there aren't a ton of uses like the converging lens that I can list out to you, and you'd be like, oh, okay, that makes sense. That makes sense. Because very rarely do we put a piece of glass over something to shrink it, to make it look smaller. But that is what this does. So they are pieces of glass that you can put on top of something, like a magnifying glass, except for it doesn't magnify it, it shrinks it. So everything still looks the same as it did on the page or the ruler or whatever, but smaller. Okay, and like a magnifying glass, you can't capture it on a screen. It's just sort of floating in that space so that you see it, but can't put it on something. Okay. One of the most common places to use this piece of glass is in eyewear glasses. And because we talked about how nearsighted, farsighted, in one of those circumstances, you need this kind of lens in front of your eye to spread the light rays that are headed towards your eye out a little bit so that when they hit your eye, they come together to perfectly hit the retina and the image is in focus on the retina. Okay, so maybe you can go back and revisit that, but that would be somewhere that you could go to see when we've made use of this lens and makes sense to you and is a practical application of that lens. Okay, but every time you do a drawing for this, it will turn out the same like that. Okay. So it's worth you trying to do that on your own, seeing if you can replicate that. Okay, and see how that goes. So the one thing that's different here is the ray that we chose to send towards the glass that was parallel. When it got to the center, instead of coming towards this F, it went out on an angle that matches with this F because you need to spread them out. All right, and you can play around with that. Okay, that's it for the week. And I will check in with you again soon. Let me get this back up here. Keep questions coming. If I mess something up or do not do a thorough explanation or somehow something is unclear going forward so that I can make sure I clear it up for you. Okay? All right. Take care, and we'll talk again soon.